Hi students. Now I am going to give lecture on the fifth unit, plastic analysis. Okay. Um, so first I am going to give introduction on plastic analysis. So most of the structural materials have experience or undergo an elastic stage and a plastic stage while we applying the load. Okay. The plastic stage marks the stage at which an increased strain does not produce an increased stress. Okay, so this is a stress strain curve for mild steel. Okay, y-axis represents the stress and x-axis represents the strain. Okay, so this stress strain curve is of three part. The first part is elastic and second part is plastic, third one is strain hardening. Okay, in second part plastic, okay, further increase of strain will not cause any improvement or increase of stress. Okay, the stress is constant in the plastic stage. Okay, so that only they mentioned here. Plastic stage marks the stage at which an increased strain, okay, so increased strain does not does not produce any increased stress or resistance, does not produce any increased stress or resistance. The stress is constant in the plastic stage portion. Okay, the stress consequent to stretching stabilizes at a value known as yield stress. Okay, so the stress corresponding to the plastic stage is termed as yield stress. Okay, so an important 2 mark question, what is meant by yield stress or define yield stress, they will ask. So yield stress is nothing but the stress corresponding to the plastic stage. Okay, the stress corresponding to plastic stage is termed as yield stress. In plastic stage, the stress is constant throughout. Okay, but in elastic stage and strain hardening stage, the stress varies. Okay, in beams, yielding can take place both under bending tension and under bending compression. Okay, when a beam yields in bending, an increase in curvature does not produce an increase in moment of resistance. Okay, yield stress only. Analysis of beams and structures made of such flexural members is called plastic analysis. Okay, so plastic analysis is nothing but in plastic stage only we are considering. Okay, plastic analysis can tell us at what load a structure will collapse. This will help us design structures for a desired safety factor on limiting loads. Okay, this safety factor is usually termed load factor. Okay, so this is one more 2 mark question, load factor. Okay, the limiting loads for a design of a structure to consider safety one. Okay, this limiting load or the limiting factor is termed as load factor. Okay, next we'll see the terminologies. Okay, so this is a graph, stress strain curve for mild steel. Okay, so stress strain curve for mild steel, we all know the y portion, y axis consists of stress and the x axis consists of strain. Strain is denoted by epsilon, stress sigma. Okay, the stress is gradually increases once it reaches the elastic stage or reaches the elastic limit, it comes under the plastic stage. Okay, the plastic stage extends further while we are applying the load. Okay, but there is no increase of stress. So after this is also up to a certain limit. Okay, after reaching that limit, the strain hardening stage will comes. Okay, the strain hardening stage also increase. Okay, once the load is increasing. Okay, it reaches the ultimate load, then it comes down and then it reaches the breaking load. All we know this stress strain curve for mild steel. This is the actual stress strain curve. Okay, and this is the idealized stress strain curve for mild steel. Okay, this is an idealized one, perfect one. Okay, same stress denotes y-axis, strain denotes x-axis, and this is the yield stress sigma y. Okay, next topic, plastic bending of beams. Consider a section. Consider a section of beam shown in figure 8.2a. So 8.2a, they are consider an imaginary figure. Okay, this is the cross section of a beam. This is an imaginary one. Okay, so consider a section of beam which is symmetrical about one axis. Okay, So they consider this figure as a beam. Okay, so this figure is an imaginary, is a symmetrical about one axis, that is y axis. Okay, if we cut this portion into two pieces and we superimpose, means it will match. Okay, so this is symmetrical about y axis. Let the beam be subjected to increasing couple. Okay, that means we are applying moment slowly, gradually we are increasing the moment value. Okay, increasing couples. When the moment is in the elastic range, when the moment is in the elastic range, that means the load is in the elastic stage, like that only. When the moment is in the elastic range, both top and bottom fibers will be subjected to stress less than the yield stress. Okay, when the moment is in the elastic range, okay, you look this graph. When the load is in the elastic range, means the stress will vary. Okay, when the load is in the plastic stage, means the stress is a constant one. Okay, so the stress corresponding to plastic stage only we are calling as a yield stress. Similarly here, when the moment is in the elastic range, both top and bottom fibers will be subject to stress less than the yield stress. Okay, that means the stress is in the elastic range only. Okay, when the moment is gradually increased, further increase means the stress pass to the plastic stage. Okay, when the moment is gradually increased, at one stage the most distant fiber, okay, maybe bottom fiber, will reach the yield stress. Okay, that is in the plastic, it comes to the plastic stage, it will reach the yield stress. Now the first yield is said to occur. Okay, the moment corresponding to this stage is called the yield moment. Because of the moment, the yield stress occurred, so the moment is named as yield moment. Okay, that is the moment at which the first yield occurs is called yield moment. This is one more important to mark, my yield moment, my. What is meant by yield moment, or define yield moment, they will ask. Okay, so the yield moment is the moment at which the first yield occurs. Okay, is termed as yield moment, my. Okay. Next, when the moment is increased beyond the yield moment, okay, further increase of moment, okay, the fiber which is already yielded will stretch further but will not take any additional stress. Okay, so further increase of yield moment, the fiber which is already yielded will stretch further. Okay, but will not take any additional stress. Okay, so this is a graph. Okay, this is a cross section of the beam, and this two graph B and C are denotes the elastic stage. Okay, so elastic stage, the stress is less than yield stress. Here also the stress is less than yield stress. Okay, the next stage D and E graphs shows the elastic plastic. Okay, that means at that time the beam consists beam is of both stage, elastic stage and plastic stage also. So here they mentioned sigma is equal to sigma y. Okay, in the middle portion or bottom of the portion only the stress happen. Okay, so the figure changes here. Okay, at the bottom and here also. Okay, the bottom or middle of the fiber only gets to change. Okay, strain will occur at the middle. Okay, so hence the adjoining inner fibers will start yielding. At a certain stage, the top fibers will also reach yield stress at a certain stage. Okay, at a certain stage only the top fiber will also reach yield stress. Okay, so a shifting of neutral axis will takes place on applying moment any further. So a shifting of neutral axis will also takes place on applying of further moment if the section is symmetrical about both the axes. Okay, this is one more important point. If the section is symmetrical about both the axes, there will be no shifting of the neutral axis through the process. Okay, here the beam is symmetrical about one axis only, that is y axis. Though shifting of neutral axis will takes place. Okay, but if a figure or a structure is symmetrical about both axes, means there will be no shifting of the neutral axis. Okay, when the moment is further increased, the yield from both top and bottom will spread towards the inner fibers. Okay, so the yield first we occurred in bottom only. Okay, so further increase of the moment will not cause any damage or further increase of stress. Okay, further increase of moment, stress or strain will occur or transfer to throughout all the part. Okay, that only they are mentioning. When the moment is further increased, there will be a stage at which all the fibers from top to bottom of the section will completely yield, and the section would not be able to take any further movement. Okay, so final movement or initial breaking movement will occur. Okay, so the resisting movement corresponding to this fully plastic stage is called plastic movement. This is another 2 mark. Okay, so yield movement, what is meant by yield movement or define yield movement, and when will the shifting of neutral axis will not occur, this is another 2 mark. Okay, and the final 2 mark, plastic modified plastic movement or what is meant by yield movement. Okay, the resisting movement corresponding to the fully plastic stage is called the plastic movement. The resisting movement is nothing but stress. Okay, so plastic movement EMP. So we all know this equation is taken from the bending equation. M by I is equal to sigma by y is equal to E by R. Okay, so they take these two terms only. So M by I is equal to sigma by y. Okay, so My is equal to why they mentioned the My yield moment. Okay, so My is equal to sigma y into sigma y into I by y. Okay, so My is equal to sigma y into Z. Z is nothing but I by y. Okay, is that is termed as elastic section modulus. Okay, this is also another important 2 mark. Define elastic section modulus, or what is by elastic section modulus, they ask. So it is the ratio of moment of inertia to the yield stress. Okay, so y is nothing but off of the neutral axis, not yield stress. Okay, elastic section modulus defined as the ratio of moment of inertia to the off of the neutral axis y. Okay, sigma y is termed as yield stress. So next topic, fully plastic moment of the section. In that we'll see the assumptions made to evaluate the fully plastic moment of the section. Okay, the first assumption is plane transverse section remain plane. Okay, the section should be remain plane and normal to the longitudinal axis after bending to the effect of shear being neglected. Okay, so the plane section should remain plane even after the bending. Okay, the effect of shear and all, they are neglecting one. Okay, second assumption, modulus of elasticity has the same value in tension and compression. So E value should be same in both tension and compression. Third one, the material is homogeneous and isotropic in both the elastic and plastic state. Okay, so the material should be made up of a single material and isotropic throughout the length of the material of the same size. Okay, fourth one, there is no resultant axial force on the beam. Okay, that is total compression is equal to total tension. Okay, so no resultant axial force. Fifth one, the cross section of the beam is symmetrical about an axis through its centroid parallel to the plane of bending. Okay, so this is one, the fifth one, the beam is symmetrical about an axis throughout its centroid. Sixth one, longitudinal fibers are free to expand and contract without affecting the fibers in the lateral direction. Okay, so longitudinal fibers only free to expand and contract without affecting the fibers in lateral direction. So these are the 6 assumptions made in fully plastic moment of the section. So this is also another important 2 mark. Okay,